Okay, hopefully this is not a total disaster. Question 7, let's see. We have a key to the study guide, right? What do you think are the most crucial topics? Well, I mean, let's see, number 7 here. We can get to this, I would say, in in pretty short order, right? Because it's not that far in, so I'm still kind of tempted to just go through question by question. Let's see. What do I think are the most crucial topics? I mean, that's a tricky question. I mean, because the actual final, right, is a pretty good representation, I think, of most everything that we've covered in this class. I think that I told somebody previously that that like the sound stuff won't be emphasized too much, right? Like the sound and wave stuff, it's there, and you'll have to know like the basics. But as long as you're good with the basics, like you'll be fine with that stuff. So I think that's probably a pretty unsatisfying answer because um, I'm basically telling you, hey, you should just be good with everything. But that's how it is, unfortunately, with this, right? Oh yeah. So also I have started working on like my own practice exam for you guys to do. Yeah, I'm recording. Thank you. And I can send that out as soon as it's done. I'm up to like 20 questions right now, and I'm really having a hard time getting like the last 5 written. But maybe tonight. But you know, at work, like absolute latest tomorrow sometime, and we could go over it during the review session tomorrow. Okay. Most of the questions are more just figuring out the concept, and the algebra is pretty quick, right? I mean, that's like I would say that if that's how you feel about this practice exam, then that is how it's going to be for the actual final, because this is literally a final that was given in previous semesters, right? Okay, let's get into it then. So planets A and B have the same uniform density as one another. I'll zoom in a little bit just in case. But planet B is twice the radius of planet A. In terms of the acceleration due to gravity on planet A, what is the acceleration due to gravity on planet B? Okay, so the first thing we need here is the volumetric density. So volumetric density. Now this I think we usually call rho, and it's just a mass over volume, right? Because this we feel like is going to be something using Newton's law of gravitation, and that depends on the mass, right? Of what depends on mass is, and so we need to just come up with a way to get the mass of these planets in terms of their density, right? Because we don't know. Let's say we don't know their mass explicitly. So this tells us, right, that the mass is given by rho v, and for a sphere, right, which is what we're going to treat these as, the mass is just going to be rho times 4/3 pi r cubed, right? So remember that the gravitational acceleration at the surface of a planet can be found by just saying that the gravitational force there that we think of, like this mg, is equal to the force given by Newton's law of universal gravitation, right? So for planet A, it would look like this, where, let's see here, we should write that this big M is the mass of planet A, and little m is like the mass of you or whatever object you're thinking of, right? So we just drop the little m's, and we get that the acceleration due to gravity at the surface of planet A is going to be given by this expression. We need to write this in terms of the density. So this is going to be g times 4/3 pi rho r a cubed over r sub a squared, right? And we can just simplify this a little bit. Like basically all we can do is cancel a factor of, well, two factors of r in the denominator, right? So what we end up with is that this just becomes 4/3 pi g rho r a, right? And then by a similar line of reasoning, and somebody checked to make sure I didn't make any algebra mistakes there, but I think this is good. By a similar line of reasoning, we can just write that the gravitational acceleration on B is going to be 4/3 pi big G rho r sub B, right? Now we're told that planet B has twice the radius of A, so what we do is we say 4/3 pi big G rho, and then double RA, right? So this works out to be 8/3 pi G rho RA, right? And so I'm getting that it should be double, right? Because we see that 2 GA equals GB, right? Is that what we're supposed to get here? One is E. Yeah, okay, we're good. So it's double, right? Just by this. And so the weird thing here is maybe just using the definition of volumetric density to write out the expression for the gravitational acceleration. Yeah, and I would definitely have all the equations on my, all the constants on my equation sheet, because again, like they're not given to you in this document, and this is, you know, a final from previous semesters. Okay, cool. All right, number 2. And stop me if there are any questions about what we just did here, but hopefully that was clear. Okay, number 2. A 0.26 kilogram block oscillates horizontally on the end of a spring with some spring constant. If the system has total mechanical energy, 5.8 joules, then what is the amplitude of the oscillation? So here is an example of where you're given information that you don't necessarily need, right? Because like I think we'll see that we don't need the mass here. We just want to remember that for SHM, let me say for horizontal, SHM with no damping, the total mechanical energy, and I think we talked about this during the previous review session, right? It's just 1/2 Ka squared. So what we do is we just solve this for A, right? And we should find that A is the square root of 2E total divided by K. If I can do algebra, that should be good. Let's check this. Okay. Square root of 2 times 5.8 divided by 290. So 0.2, right? This is going to be in meters because our spring constant is in newtons per meter, right? That's where these meters come from. Also, there's meters baked into the mechanical energy. And so we just multiply by 100 to get it in centimeters. So I don't think I need to do this, but it's 20 centimeters, right? So number 2 should be A. Let's check this, see if it's correct. Yep, 2 is A, cool. All right, hopefully this is clear. And as I keep saying, right, just stop me if there are any questions, but that's all we do for that one. Let's see, number 3 here. While riding an open freight elevator upwards at 5.1 meters per second, a carpenter drops his hammer off to the side. It hits the ground 2.4 seconds later. How far above the ground was the carpenter when he dropped the hammer? So this is going to be probably the most important kinematics equation, right? Possibly the most important kinematics equation, which was, in my opinion, this one, right, for the y position of an object. And so we just adapt this to our situation. We're saying that, let me say this. At time t, fancy t, right, is 2.4 seconds. The hammer hits the ground. So we can say it's at height 0, right? Let's call the initial height of the elevator h, or the height when where the elevator is when the guy drops the hammer, right? So, and here's the potentially tricky thing, right? Is because we talked about this also when we were making the equation sheet, but because the elevator is moving upward and the man is carrying, okay, so it doesn't have to be a man. I'm going to say it's a man, okay, but it doesn't have to be. Is carrying a hammer, right, with him, then it has the same velocity that he has, right? And so essentially this hammer is going to have a it's going to have an initial velocity vector of 5.1 meters per second pointing straight up, because the system it was in before it was dropped had that velocity, right? So that's it. This is a very important conceptual thing. So we just write that it has some initial velocity. Let's call it v naught because we're talking just about one dimension here, times fancy t minus 1/2 g fancy t squared, right? So this isn't so bad. We just get everything that's not h onto the other side. So we find that h is 1/2 g t squared minus v naught t, right? So let's just get a number for this. I know you all love numbers. You're obsessed with numbers. Actually, they're kind of important, I guess, if the format of the final is going to be like this. So, okay, I'm getting about 16 meters. All right, so let's see if that's correct. It's number 3. We thought it was A, and we're good. Yes, 3 is A. Cool. All right, so far, no mistakes. Pretty nice. Okay, number 4. A stranded cat sits at the bottom of a frictionless ramp inclined 52 degrees from the horizontal. The cat uses its mouth to hold onto a rope that pulls it up the ramp with a force of that. What is the magnitude of the acceleration of the cat up the ramp? Okay, so I will try to draw a picture for this because it's probably a wee bit important. So let me do my best. Okay, so this is my cat, right? There is a force, a tension force pulling it up like this. Right, and then gravitational force straight down. Like so. We know that this angle is theta. And we just need to wow, Wow, I'm flattered. We need to figure out what the component of the gravitational force here is that opposes the tension force, right? And so the way that we do this is we just do a little bit of trig. And this. So this angle is also theta, right? If I could draw better with my mouse, it might be clearer. And if you don't see that, let me know. But this angle is theta. And so the component of the gravitational force that opposes the tension is going to look like that, right? So we want to think about the sign of theta here. So what we should find is that T minus mg sine theta equals ma. And this is not so bad because we're talking about the acceleration of the cat along the surface of the ramp, right? And this really just amounts to dividing both sides by m. So we see that a is t minus mg sine theta divided by m. And let's get a number here. Okay, it's quite small, as about 0.4. Yeah, about 0.4. I don't know why this differs a good amount from what we have. But it looks like the answer is supposed to be D here. Let's see. Yep, 4 is D. Cool. So this is what you do. If the ramp is frictionless, how is the cat able to pull itself up? I think that someone or something is on the other end of the rope pulling on it, right? And the cat's just biting on the end. You know, cats, they love to bite things, right? And so it's just being dragged up the surface of the ramp. Oh, we got another cat here. Okay, cool. Cats, they ruin everything, right? So in a city park, a carousel with mass 35 kilograms and radius 1.5 meters is a horizontal uniform disc. Okay, so this is very much like that problem from the last exam, right? So let's see what to do here. Tangentially onto the outer edge. So basically what we're saying is that the sum here of the, like, if we think about the point right before the cat lands, that the vector sum of the orbital angular momentum and the spin angular momentum must equal 0, right? So we could say this, we could say J naught plus S naught equals 0, because after, right, the cat is on the carousel and it's not spinning, so there's no angular momentum, right? Let me just make this a vector and this a vector, and yes, even 0 a vector. Okay, so in here it's like it doesn't even matter, right, that we apply the right-hand rule or any of that crap, because we know that the components of the angular momentum, right, have to have opposite signs. And so we can simply write that I omega, oh god, wow, I'm a mess. This should not be J, this should be L, my bad. Okay, so what I would do is I would write RMV sine theta, right? This is what this looks like. And let's just assume that the carousel is rotating clockwise, right? So we write minus I omega over here. And we set this equal to 0. we can get rid of this sign because we're told that the cat jumps onto it tangentially, which means this sign just becomes sine of 90 degrees, which is of course 1, right? So we get rid of that. And we also need to remember the moment of inertia of a disk, which should be 1/2 mr squared. And so what we find is RMV equals 1/2 big M R squared. We can get rid of a factor of R on each side. And then we just divide both sides by little m, right? So we find that this should be oh, I totally forgot about omega. Yeah. Okay, there should be an omega here. My bad. And you know how I noticed that I forgot about it, right? Was I was looking at the dimensions of the answer I was about to get. Okay, so look, do this, all right? Think about units. So what we find, right, is that it should be, let's be careful here and write that V equals big M R omega divided by 2 little m, right? This will end up having dimensions of speed, right? Which is good because that's what we need. I think this is good. All right, let's get a number here. 35 times 1.5 times 1.7 divided by 2 times 3. Okay, about 14.9 meters per second, right? So we think number 5 should be E. Let's see if that's correct. It is, cool. Okay. Number 6. Wagon of dog treats combined mass, blah, 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 is rolling at 2.1 meters per second. A dog with mass 21 kilograms dives into the wagon, colliding with just enough momentum to make both stop. Okay, so we know how long the collision lasts, and so we just need to figure out what the average force is that the dog exerts on the wagon. No, exerted on the dog by the wagon. Whatever, it's the same thing. Okay, Newton's third law, right? Let's see here. Okay, so the initial momentum of the wagon is just going to be, let's say P naught, and this is a one-dimensional thing, right? Remember, momentum is a vector, linear momentum is a vector, and you need to remember that, but for this situation, it's just fine to work in one dimension, so that's what we'll do, and we'll say that the initial momentum is big M. So big M is the 55 kilograms, right? And let's say that it's rolling at V naught. So V naught is the 2.1 meters per second. We know actually that the final momentum of the wagon is 0, right? Because it comes to a stop. So putting this together, we see that delta P, right, is just going to be the final momentum minus the initial momentum, so it's going to be negative m v naught, right? And so then impulse momentum theorem gives that delta P equals average force times delta t, right? Like this. And so from this, we find F bar is just delta P over delta T. And this equals negative M V naught over delta T. Now, you might be wondering why I'm getting a negative sign here. Well, you probably aren't, because actually I just talked about this, right? I just talked about how momentum is a vector. But I just want to stress that that when I wrote this, I made a choice basically that the wagon was rolling in the positive x direction to the right, and that the dog jumped at it to the left. Okay, so you shouldn't be alarmed by the negative sign here because we're asked about a magnitude. But if you think about this as it would happen, right, with the wagon rolling to the right and the dog coming in to the left, the force that the dog exerts on the wagon should be to the left. And by Newton's third law, right, this has the same magnitude as the force that the wagon exerts on the dog. And so this is fine. So we'll see what number this works out to be. So 55 times 2.1 divided by delta t, which is 0.1. It's about 1.16 kilonewtons, right? Because you just divide this by 1,000 and you get it in terms of kilonewtons. So we think 6 is E. Let's check this. And indeed it is. 6 is E. Amazing. Okay, so here's what I want to talk about though strategically, right? And I've mentioned this, but like, look, here's an instance of Dr. Nero giving you information that you don't need, right? He tells you what the mass of the dog is, and that never appeared in any of our equations. So you got to be careful with this stuff, right? I don't think that Hatridge or any of the other people who are writing the exam are going to be in the habit of giving you information you don't need, right? Because there's like 3 or 4 different instructors who put the exam together. I think like maybe there are 5 and each of them wrote 5 questions. But just be on the lookout, right? Because sometimes you might have information you don't need. And if you feel good about the work that you've done and you didn't use one little, number given to you in the problem statement, it's probably okay, right? Now, if you're doing like most of the exam without all the numbers given in the problem statement, that's probably cause for concern. But, a few here and there is okay. Okay, so number 7. Car is right on the verge of sliding as it speeds around a level circular track. The radius of the track is 21 meters and the coefficient of static friction between the car's tires and the track is 0.7, while the coefficient of kinetic friction is 0.56. So here's another thing, right? We don't need 2 coefficients of friction here. So like I was saying, but this is just going to be Newton's second law for circular motion, right? And so what we want to do is we just want to write that the net force in the centripetal direction equals some stuff, which then equals mv squared over r, right? And so we just have to fill in basically what is the centripetal force in this case. And we're already kind of like led to believe that it's going to be one of these forms of friction. And I'm going to say that it's going to be static friction because there is no relative motion in the centripetal direction for the car, right? Because if it's staying at a constant distance away from the center of some circle, then it's not obviously accelerating in or... No, I shouldn't say it like that. it's not sliding out, right? And so here we just write what this is just a static friction force, right? And we want to remember that the maximum value here, and we are licensed to use the maximum value because the problem statement says the car is right on the verge of sliding out. So we just write that it's mu sub s times the normal force. In this case, normal force is just mg, right? You could draw a quick free body diagram to convince yourself of that. And then notice that we can cancel masses here, right? There's an m on each side. We can just get rid of those. And we would expect that because we don't have a mass for the car, right? And so this tells us that v squared equals mu sub s gr, right? So we just take the square root of that. Hello? Where is Mathematica gone to? Okay, so we need to do square root of 0.7 times 9.81 times 21. And so I'm getting pretty close to 12 meters per second. So we think it should be C. Oof. Okay, this is annoying. There we go. So 7 is C. Yep, 7 is C. Cool. So I think that was Lauren who's asking about number 7. Let me know if that was clear or if you need me to explain any further. Yeah, so it's static friction because it's not. Because the car isn't sliding, right, in the centripetal direction or the centrifugal direction, right? It's not sliding in or out toward or it's not sliding toward or away from the center of the circle, right? Because it's on a circular track, and that leads us to interpret this as it's moving in a circle. And so it has to be at a constant distance from the center of the circle through which it's moving, right? That's just because geometry. And so while there's relative motion between the tires and the pavement, okay, imagine this, right? You're driving the car and you're about to skid out, you know, or you feel like you're about to skid out. You're definitely moving like forward, like say you're looking straight ahead, right? You're moving forward, but you're not moving to the left or the right because you're not sliding out. You're not sliding in. And so there's no relative motion in that direction between the tires and the pavement. And if it were already sliding, it would be kinetic. Yeah, if it were already sliding, it'd be kinetic, yeah. But I want to say that for problems like this, it's almost always going to be static friction, right? That seems to be the trend for these like highway curve problems. Maybe I'll throw one of these on the exam that I'm working on because I don't have anything like that. You can do that, yeah. Okay, let's see here. Number 8. A moving van is loaded with furniture until its center of gravity is located 0.25 meters in front of its rear axle. Total mass of the loaded van is 2,400 kilograms. The separation between the front and rear axles of the van is 2.5 meters. What is the magnitude of the normal force from the ground exerted on the front axle of the van? Now, this is a torque problem, and it's very sort of disguised. And I think I'm going to have to do more drawings for this, so just bear with me here. But at least, what? Okay. I know the color is blue. Oh, it's like I see what happened. Okay, let's do this one more time. There we go, okay. So let's make a sketch here, a very crappy sketch. This is my van, right? And at least this way I can like use the shapes, which is not so bad. There's like a wheel here. No. Oh, okay. And a wheel here. Right, and the axles are right above these, so that's how we're looking at this. Okay, so center of gravity is located 0.25 meters in front of its rear axle. So the center of gravity might be like here. And the separation between the front and rear axles of the van is 2.5 meters. So we'll call this D. And this is the distance between the axles. Okay, and then we'll call this L, I guess. Okay, bear with me because I do need to do a little bit more drawing here. We have to draw in the normal forces. Let's see here. Ground exerted on the front axle of the van. So, I mean, these normal forces have to point up. So there's a normal force here. We'll call it N. Front. And then there's a normal force here. We'll call it N rear. And then the point of being told about the gravitational or its center of gravity is that you have to remember to put, and this is something that I think people struggle with the most with this stuff, is you have to put the gravitational force in. So the gravitational force points straight down as usual, and it's acting at that point. So now we just sum torques, right? And we demand that the net torque about some conveniently chosen axis of rotation is 0. And I think that the most convenient choice here is to put our axis of rotation like here, I guess. Because we don't want to put it somewhere that gets rid of the force that we actually care about solving for, right? We care about solving for the normal force at the front. So we need to make sure that we don't get rid of that. So then, shouldn't be so bad from here. I think most of the work here was just drawing the diagram and convincing you all that it makes sense if you believe that it does. Let me do this. I'm going to fill this in my other monitor here because I don't want to. I don't want anybody to have any issues seeing it when it's done. So just let me do this. So we have this force, right, will tend to make it, the gravitational force will tend to make this thing rotate clockwise. So we should make it negative. And the normal force will tend to make this, the front normal force will tend to make this rotate counterclockwise, so it should correspondingly be positive, right? And we set the net torque equal to 0, because it's not rotating about the rear axle. And so this is our equation, and we find that the normal force at the front should just be mgl over d, right? And this dimensionally makes sense, right? Because mg is a force, L has dimensions of length, and d has dimensions of length. So we wind up with something that has dimensions of force. So what do we do here? We just do 2,400 times 9.81 times 0.25 divided by 2.5. And we get about 2.35 kilonewtons, right? So part A here, or choice A for this one. Let's see what we think. Yep, 8 is A, cool. Okay, moving on. 9. Wheel experiences an angular acceleration of 4.3 radians per second squared. After making 6.6 revolutions, it has an angular speed of 45 radians per second. What was the wheel's initial angular velocity? So this is almost like a one-liner, because what we can do is we can just write omega squared equals omega naught squared plus 2 alpha delta theta, right? But we need to remember to convert the angular displacement from revolutions to radians, right? So this is like the one possibly tricky thing about this. So we'll just talk about how you do this. And everybody probably knows, but I'll just do it. So it's 6.6 revolutions and 2 pi radians is 1 revolution. And so it's just going to be 6.6 times 2 pi for what you plug in for delta theta here. Everything else is, I think, is fine, right? So you just do the square root of both sides. So let's get a number, I guess. Square root of... oh, wait, no. We have to do this. Because we want initial. So we just have to write that omega naught squared equals omega squared minus 2 alpha delta theta. Now we can do this. So we want the square root of 45 squared minus 2 times 4.3 times 6.6 times 2 times 2 pi. Oh, wow. 2 pi. I think this is good. $40.8, and that's a choice, right? That's choice D here. So let's just check this. It is D. Yep, 9 is D. Cool. Okay, everybody's favorite topic now, relative velocities, right? We love these. What I would say here is it's a good idea to make a sketch. So I think I'm gonna have to make another crappy drawing. So we can do this. We can make like our coordinate axes. This is obviously going to be Y. It's going to be X. And I think it's just a good idea to draw these vectors out. So we'll do blue for the dog. Color 1. Oh my God. Okay, blue for the dog. And it is running north, right? So remember, north corresponds to the positive y direction. So its velocity vector looks like this, maybe. We'll call the dog U. And then the cat it's chasing flees at 7 meters per second at 49 degrees north of east. So that's going to look maybe like this. And we'll draw this longer because it's much faster than the dog, right? So v for the cat. What is the cat's speed with respect to the dog? So this is going to be just taking... Let me do this though. Theta. So this is just going to be subtracting off basically the dog's velocity from the cat's velocity. And so for this, let's do this, subtract the dog's velocity from the cat's velocity. And here's something we can note maybe immediately, right, is that the x component of their relative velocities will just be the cat's x component of velocity, right? Because the dog is not moving to the right or in the positive x direction, it's just moving up. And the cat has a non-zero x component of its velocity. So what we do is we just write, and we're actually talking about vectors here, right? We're not talking about speeds yet. Let's do v minus u. Now, we do this as an ordered pair, I guess. So for the dog, it's going to be, well, let me put in the dogs also. Okay, so for the cat, it's going to be v cosine theta for the x component, v sine theta for the y component. And now the dog is just going to be 0, comma u. And so this equals v cosine theta, v sine theta minus u. And then we just want to find the magnitude of this, right? We want to find v minus u, because the difference of two vectors is, of course, a vector. And, okay, how did I figure out the v minus u again? Yeah, this is the tricky part, I suppose, but it's like, it's basically that we want to figure out what the cat's velocity is above and beyond that of the dog. Because we could imagine a situation where the dog is standing still and the cat is running in some way such that the relative motion between them is the same as it is in the actual situation, right? And this is all relative velocities are. It's like basically force one of the objects to be stationary and then adjust the other's velocity so that the relative motion between them is the same. That's all this is, right? And again, you know, like I think that we talked about this last time, but it's like you just think about some situations where like you and another person are walking toward each other and you intuitively know that the distance between you is closing the fastest it could, or you think about you walking towards another person who is stationary and the distance is closing at like, you know, a medium rate, I suppose, or you walking towards someone who's walking away from you and the distance would be closing at like the slowest possible rate, right? Because I mean we just know these things intuitively. That doesn't mean that it's easy to show with the math, right? But in general, these relative velocity things will either be just subtracting or adding the two vectors, right? That's usually what it's going to be. I think it's always what it's going to be. And you just have to know when to subtract or when to add, right? So like in the case of two objects moving toward each other, you would add. Or in the case of two objects moving away from each other, you would wait, no. Hang on. This is tough to put into words, but I am correct, right? And I stand by my statement that it will be adding or subtracting the vectors together. But it does depend because you sort of have a few different possibilities, right, as far as the relative motion between them goes. But like, let me just finish solving this, and what we'll see is that this is like the case, this is physically equivalent to the case where the dog is standing still and the cat is running in some other way that we've adjusted now that the dog is standing still. Okay, let me maybe try to do this that way. So what we do, right, is we just do the Pythagorean theorem here. Plus v sine theta minus u squared. So it could be easier to look at components and then add the components in opposite directions and subtract the components in the same direction. Yeah, that's what we're doing. That's great. That's it. Cool. So I'll just make Mathematica do this. Like, why does it keep hiding though? That's super annoying. So let's see, square root of v times cosine theta squared plus v times sine theta minus u squared. That's what we have, and then we'll just put the numbers in. So we said u was 2.4, v was 7, and theta is 49 degrees. So 5.42, right? Choice C. Let's check if this is correct. And it is. Now, this is, despite being a relative velocity thing, kind of a nice problem, because like you might notice that if we had done this the opposite way, like if we had subtracted v from u instead, we would have gotten the same answer. Because math, right? Because this is also equal, incidentally, to u minus v. Right? And this is a good thing to remember. But we would have gotten the same answer if we did it the other way. So it is kind of just knowing about when to add and when to subtract. Like was said in chat. Is this helpful for this one? I mean, you could talk more about it if this stuff is unclear, but are we okay with this idea with the relative velocity stuff? I'm going to move on, but if we need to come back to this, we can. Now, number 11 is funny, right? Because, let's see, a tuning fork produces sound waves of wavelength lambda in air. The sound is used to cause resonance in a pipe that is closed at one end and open at the other. The length of this pipe cannot be, right? Look at all these choices. One of these is not like the other, right? And it's C, because if you look at A, B, D, and E, they all have odd numbers in their numerators, right? And so this one, like, I'm pretty damn confident is C, just because it just has a different form, right, than all the others. And this is another thing, you know, that you want to think about when you're taking an exam that's multiple choice, right, is like maybe you have no idea how to do something, but like just look at all the possible choices and see, right, like if there's a pattern or if there's not. So let's see if 11 is in fact C. And it is. 11 is C. But we can talk about this really quickly. Give me 1 second here. I think this was the thing that I found that I liked. And so we have a tube that is, a pipe that is closed at one end and open at the other, right? And this is, we talked about this during the last session, right? But this is, what do we want here? The length, okay, yeah. So the length here is, it must be n lambda over 4, where n is an odd integer, right? And so this is just kind of a pattern seeking sort of question, right? And I would hope that if there's something like this on the final, everybody gets it. Do we need to talk about 11? If so, somebody can just say so, but I'm going to leave it at that. Okay, 12, so two balls with masses 170 grams and 340 grams make a head-on collision. Before the collision, the speed of the 170-gram ball was 6.1 meters per second. After the collision, the total kinetic energy of the system is 9.8 joules. What was the initial speed of the other ball? Okay, so what we do, right, is we just, I think here we can, well, we can definitely apply conservation of energy because it's elastic, right? So conservation of energy, we want to just look at the initial kinetic energy and the final kinetic energy. And for the initial, I'm going to write 1/2 little m, right? Little m will be the mass of the 170-gram ball, u naught squared plus 1/2 big M v naught squared. And let's see here. Before the collision, the speed of the 170-gram ball was 6.1 meters per second. So we know the final kinetic energy, it's just K, right? We'll keep that as it is. It's 9.8 joules. And so to find the initial speed of the other ball, we just solve this for V naught, right? 9.8 joules. Yeah, that's it. So I'll just do this here. We can multiply everything by 2, which is a good idea when you're working with a problem like this. This equals 2k. Then we subtract m u naught squared from both sides because that is what we know. All right, so let's see here. Big M v naught squared equals 2k minus m u naught squared. And pretty much the last thing to do is just divide both sides by the mass. So we get v naught squared equals 2k minus m u naught squared divided by big M. And then we would obviously have to take the square root of whatever this works out to be to get the correct answer. So let's do this. Okay, so 2 times, what was it? 9.8, yeah. 2 times 9.8 minus 0.17, right? We have to remember to convert from grams to kilograms, but that's just dividing by 1,000. Times 6.1 squared divided by 0.34, and then square root. And we get 6.25-ish, which is A. So that's cool. Let's see if it's correct. Yep, 12A, cool. Okay, was that good? Everybody okay with this one? If not, like I keep saying, just stop me. We'll look at it a little bit more thoroughly. Okay, 13, a kiloton of energy or a kiloton of TNT is an energy of 4.184 times 10 to the 12th joules. How much mass would an object have to acquire a kinetic energy equal to 1 kiloton of TNT after being dropped from 640 kilometers above the surface of the Earth? Yeah, so here, like, where you're being told about the mass and radius of the Earth, it's kind of like a dead giveaway that you have to use the more precise version of the gravitational potential energy, right? So this is what we do. We still apply conservation of energy much as we would before, but we have to be more careful now, right? Because we're using the different version of the gravitational potential energy. So how I would write this is negative g, big M is going to be the mass of the Earth. Little m will be the mass of the object, right? That's what we want to solve for here. How much mass would an object need to have to acquire a kinetic? Okay, we want to solve for the kinetic energy. So this is going to be, I would write r plus h. So big R is the radius of the Earth, and h is the 640 kilometers. Now, you need to be careful with this because it looks very much like the expression for the force from Newton's law of gravitation. And so what you don't want to do, obviously, is square this. And I would bet, right, that one of these answers maybe corresponds to deciding to square this, and then probably on the other side too, right? And so this is just like what I was saying, where if you get the correct, or if you get a number that is one of the choices, it doesn't necessarily mean you're right. So you need to, you know, be vigilant, right? So K is just going to be the kinetic energy. It's going to be 4.184 times 10 to the 12th joules. And then here we're going to add, well, subtract sort of the gravitational potential energy that an object would have at the surface of the Earth, right, at sea level, basically. And so what we find is that K should just be, we can be fancy and factor, wait, no, we want to solve for the mass though, don't we? I guess we should still do that though. We want to get all the terms involving the little m on one side, right? Because remember, little m is what we're solving for here. Big M is the mass of the Earth. So I'll just do what I was going to do. G, I won't try to factor though. At least not yet. So this equals K. I guess I do want to factor though. Just not the way that I thought I did. So we factor out little m, and we find big G big M over big R minus big G big M over big R plus H equals K, right? And therefore the mass must be, that's not what I meant to copy, but that's fine. K, this is what I meant to copy, divided by all this crap, right? And let's get a number here. Where did you not plus your equals U plus K come from? This is just conservation of energy, right? This is just saying that initially it has like a bunch of gravitational potential energy, and then when it's at the surface of the Earth, it has kinetic energy by hypothesis, right? Because we need to figure out what the kinetic energy is. But it still has gravitational potential energy because of this more precise formulation of the gravitational potential energy, right? It would probably be tempting to set equal to 0, but it's not. It can't be 0. Let me know if that answers the question thoroughly. But we just have to evaluate this. And I'm going to do it like this. I'm going to have it take the expression, and then I'm going to plug the numbers in. It's easier this way. Yeah, K0 is 0. It's sort of, you know, maybe a little ambiguous here, but they say dropped, right, from that height, so it's kind of reasonable to interpret that as it having no, initial kinetic energy. Cool, so let's see what we get. We get K, oops. K is 4.184 times 10 to the 12th. G, what the hell is G? I think it's 6.67 times 10 to the negative 12th. Let me check this. Ooh, negative 11th. Okay, I was close. Thank you. Yeah. Negative 11th. Numbers, right? Who gives a damn? Mass is 5.97 times 10 to the 24th, and big R is 6.37 times 10 to the 6th. Yeah, we don't need no damn numbers. And H is given to us in kilometers, so we have to remember to convert, right? So we just multiply it by 1,000. I think this is good. And so, okay, so we get 7.33 times 10 to the 5th, which is a choice, so that's encouraging. Let's make sure that it's the right one. 13 is E, yes, cool. Okay, number 14. We love Young's modulus, right? Heavy crate with weight 4,900 newtons hangs from a thick nylon rope, cross-sectional area. What is the strain on the rope resulting from the crate? Okay, so you remember Young's modulus, right? And if you weren't here for the last session or didn't watch the video, I'm going to call it Y. Okay, I don't know why they call it E. I think that's stupid. It's just the stress, which is the force over the area, divided by the strain, which is not that delta. Basically, the fractional change in length of the object that we're thinking about here, right? And so what we want to solve for is the denominator here, right? This thing. And so we would find that delta L over L naught is F over A divided by y. And I don't like this. Okay. So this is what we need to evaluate here. Which is just f, and it did it again, over a, right? All right. We'll get a number. So the force actually on it, we should think about this, right, is just going to be the weight of the crate. In case that wasn't clear, that's all we need to do for that. So it should be 4,900 divided by 3.7 times 10 to the 9th times 1.4 times 10 to the negative 4th. And it's very small, right? If we're correct. I'm actually not super confident about this because, like I keep saying, physicists don't give a damn about this stuff, but let's see if we're right. 14 is C. Yes, it's C. Okay, amazing. Yeah. Okay. I think that I might just do 15 and then stop here for the night, because I do still have like my own assignment that's due at midnight that I need to put a good deal of work into. But tomorrow I don't really have any time constraints, so we can, you know, if we feel like we want to, we can finish up the rest of these questions, or we can forget about them and move on to the practice exam that I'm going to prepare. So let's just do this and then call it for the evening, I suppose. So I'm not comfortable with this stuff, so I want to be very careful here. Thank you. Yeah, I don't know. Like, I feel like it's a disaster, but maybe it's better than I think it is. We want the amplitude is going to be 4.5 centimeters, and here it's a good idea, right, to I think just always convert everything to the base units. Sometimes it won't end up mattering, but like in general, it doesn't hurt. And we have that lambda, right, is going to be 10 inverse meters. And the frequency, right, we want to write F here because it's given to us in hertz and not radians per second or just inverse seconds. Is this I probably shouldn't even be stressing about this paper that much, because like he's making it due at midnight, and I mean he has to have our grades in by Monday, and I don't know, each paper's like 10 pages. I don't even know if he's gonna read them, but I have to be safe, right? So let me just look up this equation because I can't remember. Tension strain. Let's see what comes up. This is the one that I'm thinking of, right? Is this? This would be. I don't know if did we talk about this? I think we did during the last session, but this would be a good equation to definitely have on your equation sheet, right? And so we would write that F is, before I do this, I'm actually just going to put this into Mathematica and make it clean it up for me, because I don't like the way they've written this. So that's that. I just want to power expand this, make it nicer. Okay, so what we find, right, is that this equation can also be written as 1/2 times the square root of t over ml, which I think is a little nicer looking than what they give us here. Though I can't be mad at hyperphysics because it's basically the best. But this is, I think, a little bit cleaner looking. And let's see what we got. Wait a minute, though. Can we just do v equals lambda f here? Does that work? Am I overcomplicating this? And this is not, you know what, I'm insane. This is not lambda, I'm sorry, this is k. Remember, wave number is k. Yeah, so I think that actually this is just v equals lambda f. And if I said that during the last video, then I have serious concerns about my mental state right now. But I think that's all we do here. And see, like, look, he threw me off, right? If this is correct, he gave us the amplitude. And I was like, oh, amplitude, we need to use that. But yeah, right, like, it seems like this is probably what we actually want to do. We just have to remember that the relationship between lambda and k is such that one is 2 pi over the other, right? So to get this in terms of k, we just write that lambda is 2 pi over k f, right? So we find that it should be 2 pi f over k. You know, no, it's good that I mentioned that equation, though, because I think that that's a good one to have on your equation sheet that maybe I didn't discuss last time. And so I would recommend that if you didn't put that on your equation sheet, you should. So let's see what this is, though. 15 over 10, right? Yeah, 17 pi fifths. That's okay. Which one of these? All right, give me a number, you smartass. 10.7 meters per second. That was choice A. Yep, 15 is A, so it is just v equals lambda f. Okay, so the moral of the story here, right, is don't let them trick you by giving you irrelevant information, right, which is, in this case, the amplitude. You didn't need it. And so that's the moral of the story here. Okay. You know, I have to just do my usual advertisement. If you haven't followed the stream yet, basically, you're a thief. You are stealing from me, and I'm going to report you to Twitch police. No, I'm kidding. It's not a big deal. But if you don't mind, right, it's free for you. Just hit follow, and then that way you'll be notified when I go live tomorrow. No, I don't get paid for this. You'll be notified when I go live tomorrow. And you know, if I am TAing for 175 next semester, I'll probably continue to do this. So it's not just going to be like a one-day thing potentially. But yeah, it's a bit. Yeah, it's a bit. Hopefully you thought it was a good one. But that's it. All right, I'm going to stop recording.